Now in this problem, we're given that the dollar-weighted rate of return is equal to 10% precisely. And then using this information, this is the entire, all the cash flow that happens from June 30th of year 10 all the way to June 30th, year 11. So we're given all this information. And now we need to find the time-weighted rate of return. So for convenience sake, I've copied out the table over here. And so first of all, in order to find the time-weighted rate of return, we need to know x. And then to find x, which is the final amount that we will have at the end of the year, we will use the information that the dollar-weighted rate of return is equal to negative 0.1. So all we have to do is just to apply the dollar-weighted rate of return formula. So 0.1 is equal to, so now we can just apply the formula for dollar-weighted rate of return. So we start off with the initial amount that we have at time 0, and then we minus the final amount that we have, and in our case it's going to be x, and then we minus the net cash flow. And then you'll see that throughout the entire year the net cash flow is equal to 0. So you have 2,000 minus 2,000 because this is a withdrawal. So minus 2,000 plus 2,000 minus 2,000 plus 2,000. So the net cash flow is actually equal to 0. And then the denominator we have this amount that we have at the start of the year, and then plus the cash flow multiplied by 1 minus the time that they occur. So you can imagine June 30th, year 10 as being time 0, this is time 1. And then September, that's 3 months into the year, this is time 1/3. So we're using month as a unit of time. So this is going halfway. Actually, not 1/3, 1/4. So this is 1/4, this is halfway, and this is 3/4. So you can divide it into, kind of like subdivide the time into these components. And then now we can apply this to the formula for the dollar-weighted rate of return. So the first cash flow that we have is a withdrawal of 2,000. So withdrawal, that's minus 2,000. And then we multiply it by 1 minus the time that occurs. So 1 minus 0, that's just 1, right? And then we plus the $2,000, which is a deposit, so it's plus 2,000. And then 1 minus the time that occurs, so 1 minus 1/4. And then we have another 2,000, but this is, again, it's a withdrawal, so minus 2,000. And then 1 minus the time that it occurs, and then plus 2,000, and then 1 minus the time that occurs. So this is the entire denominator, and all we have to do is just to calculate out this expression, dump it to the other side, and then with a bit of rearranging we can find x, which is equal to 13,100. So using this result, now we can find the time-weighted rate of return. So recall that time-weighted rate of return is just essentially treating this as one period. So this is 1 plus I1, and then this period here is 1 plus I2. This period here is 1 plus I3. This period is 1 plus I4. So this I1, I2, I3, I4 is just notation that I'm using. So this represents the in this case, well, it's a 3-month effective rate, but that's occurring between this period. And the time-weighted rate of return is defined to be equal to this expression. So this is essentially the concept of time-weighted rate of return. All we're doing is just applying this formula. So 1 plus I1, this is the effective rate that we're earning from time 0 to time 1/4, right? So the effective rate that's just the final amount that we have here divided by the amount that we originally had. So the original amount that we had at time 0, we started off with 12,000, but then we made a withdrawal of 2,000, so we're left with 10,000. So we start off with 10,000, and then it grows to 10,000. So essentially there's no growth. So I1 is equal to 0. And then we repeat the process. Now we find I2. So I2 is the effective rate of interest from the 3-month effective rate of interest from this period to this period. So from this time period to this time period. So we start off with $10,000 and then we make a deposit of $2,000. So at this time point we have $12,000 and then it grows to $14,000. So this whole expression here is 1 plus I2. And then once again, we do the same thing for the next year. So at this time point, we have 14,000, and then we make a withdrawal of 2,000. So then we end up with only 12,000. And then moving on to time 3/4, this amount grows to 13,000. So we have 13,000, and then we make a deposit of 2,000. So it grows to 15,000. And then this 15,000, it grows to x. And x that we found is equal to 13,100. So in this case, it's not exactly a growth, it's a decrease. So it is possible that this might be negative. So all in all, we just want to find the product of these four interest rates, and then this is going to chain up into a final interest rate that represents the effective rate for the whole year. And if you substitute everything into this expression, you'll find that it's equal to 1.104. So I is equal to 10.4%. So this is the answer. And if you look back at the document that I've released on Moodle, you'll see that the answer is given is going to be very slightly different. And you'll see that they applied the formula directly at the effective rate. So they're treating the dollar-weighted rate as the effective rate. So you might question whether this kind of treatment is correct. So recall that, always remember that the dollar-weighted rate of return is an approximation for the effective rate. So this is just applying the approximate interest rate to x. So the amount that you get here is an approximation, but it's a close one. So it's perfectly valid to use this. So everything that we're dealing with here with time-weighted and dollar-weighted, it's all so approximations. So it's perfectly fine to do this. So this is you could say an alternative method. So this offers you extra. So using the method that I just presented here, you're getting extra practice with the formula for the dollar-weighted rate of return. So if you find that this is slightly different, just don't worry, it's perfectly fine. And then you see that the answers are pretty much the same. So